understand something in any time of your life, look up if there's a PhET involved. So for molecular shapes, this is a really good thing. I just want to walk you through it. If you, let's do model. And the reason I like this, um, let's start with this. So you have two areas where there are electrons, and this allows you to, in 3 dimensions, see how that's all lined up. So when you have two areas that are all electrons and they're trying to get as far away from each other, right? If I kind of, well, let me try it, right? If I try to like chase this thing, it wants to get away and stay 180 degrees away. So you can see the bond angles here. You can see the name of the geometry. You can see all that. So what happens if instead of two things, there's two things with lone pair? This is like water. So you see how this is no longer in a straight line because these lone pair want to push those down. And you can see that effect by taking them away and putting them back. So that's what I like about this, is you can kind of play with it. And so you see how I add those, that makes those bend. And when I take them away, they can go straight. So that's why water is bent, but something like carbon dioxide, which was these two things, is linear. Okay? So if we have three things on there, well, let's do it this way. All right, so if we had something like carbon double bonded to oxygen with two hydrogens, do you see how those things can be all on the same plane? So that's trigonal planar. It's the shape of a triangle, and it's all on the same plane. And then if I add a lone pair, so something like ammonia, oops, whereas still, all right, three things, everything's on the same plane. If you add a lone pair, now that pushes everything down, and so now it's more of a pyramid. So that lone pair, well, that's hard to do. All right, so that lone pair sort of pushes these things down, and then you can take away the lone pair and see them spring back up and put it back and see them go back down. So you see how that happens? So that's trigonal planar, and that's trigonal pyramid. And then if I take that away and put four things, that's tetrahedral, where two things, right? This one here is coming out at you. This one here is way back pointing away from you. And then these two are that angle of 109 degrees, 109.5. So that's what I want you to do. Now, the bad thing about this thing is you can then play with real molecules, which is great. Here's water, right? You can see the bent shape of water. Here's the CH4. So the problem with assigning this is half of these molecules are things you never need to worry about unless you get into some crazy inorganic chemistry. If you're just going to deal with biological systems, water, carbon dioxide, ammonia, and methane, BF3 maybe, I guess so, and SO2 maybe. But the problem with this is you can explore all these other things. Look, xenon is a noble gas. Here it is twice reacting with fluorine. You want to talk to me about that? I am happy to talk to you all about why that happens. But it's so much easier in your life to just ignore this nonsense, because it so doesn't occur frequently enough to worry about. All you should worry about is everything wants to have 8, right? So 1, 2, 3, 4, 5, 6, 7, 8. There's 8 around that carbon, right? And water. So each hydrogen has 2 that it's sharing, and the oxygen, since it has 2, 4, 6, 8, it's sharing 2 with the hydrogens, and it has 4 on its own. So those are at 6, and then the other 2 it's getting from the hydrogen to be 8. So that's my hesitation showing you this, is that all this stuff can blow your head up. And if you want to talk about this, please email me. I'll happily discuss what's going on here, but I don't think it's important to get into things beyond the octet rule, beyond the fact that everything wants to be like a noble gas. So I wouldn't worry about it. You're welcome to play with it and see the effects of it. But these things really are sort of almost science fiction. Not really, but a little bit. Okay.